Thank you for having me here. So today I'm going to be talking about an expansion problem in Schubert calculus. This is going to be based on joint work with Qian Yu. So I'm gonna first consider two deformations of Schubert polynomials. So the first deformation we've seen earlier, which is if we consider Edelman cohomology, then we have the double Schubert polynomials, which are polynomials labeled by permutation and have variables x1 to xn and y1 to yn. Okay, and there's as seen in Tong's talk, there's a combinatorial formula in terms of bunkless pi primes that can compute these polynomials. You sum over bunkless pi primes, the weights are given by the row and column places of the blank tiles. Okay, so this is the first deformation. The second one I want to consider is to stabilize Schubert polynomials. So I'm gonna try to put fixed points in front of my permutation as much as possible, A cross W. So when I take this what is called stable limit, then I get what is called the Stanley symmetric function. And then these will be in variables, infinitely many variables whose indices are non-negative integers, Stanley symmetric functions. Okay, and then now I kind of want to combine these two deformations to obtain what is called double backstable Schubert functions. So these Schuberts, they will be labeled by a permutation, but now instead of Sn, this labeling permutation will be in Sz. I'm going to put a backward arrow on top to indicate that I'm back stabilizing, meaning that I'm going to introduce variables going to the negative direction. So now my polynomial is going to be labeled by x and y, where the indices are labeled by all integers, including the negative ones. Okay, and these represent Algebraic cohomology of what is the infinite flag variety. There's also a combinatorial model to compute these polynomial in terms of infinite size bunkless pi primes. So the border list is supposed to imply that we're tiling the entire plane, and then again, you read off where the blank tiles are, and that gives you a weight for a bunkless pi prime. And in general, there will be infinitely many bunkless pi primes associated with each permutation. So really, you get a function instead of a polynomial. Okay. And so I mentioned, so this talk is about double Edelman Greene coefficients. I first have to define to you what are single Edelman Greene coefficients, or just Edelman Greene coefficients. So I look here, I mentioned that this Stanley symmetric function is a symmetric function. So I can expand it into the Schur basis. So Fw, if I try to expand it into the Schur basis, then I get coefficients W lambda. These are going to be non-negative integers. And these are going to be counting numbers of tableaux of shape lambda, whose content is a reduced word of W. So this is the normal Edelman Greene coefficient. Okay, so double Edelman Greene coefficient, then I want to take this in expansion, but look at it in this equivalent setting. So I'm going to take my double backstable Schubert polynomial, x and y. I'm going to expand it into backstable double Schurs. So I did not define this, but you can think of these Schurs as a special case of these Schuberts when you're labeling permutation is a Grassmannian. Okay, so when I do this expansion, the coefficients I get are no longer integers. These are actually polynomials in both x and y. And then now double Edelman Greene coefficients, when I set all the x variables to y variables. So I get, so these are labeled by W and lambda as well. So if I set all the x variables to y variables, I get a polynomial with just y variables. And this is what is called the double Edelman Greene coefficient. So these were introduced by Lamley and Shimizono, and they showed some very nice positivity property of these coefficients. So they show that these J coefficients, they are non-negative spans of linear forms yi minus yj, where I is less than j in a special total ordering where all the positive numbers are smaller than all the negative numbers. So in this total ordering, I have 1 less than 2, less than all the positive numbers, and then -2 less than -1 less than 0. Okay. So you can write so they show that you can always write this coefficient in linear forms like this. And this is what I would call being positive. So in the paper where they define these coefficients and show this theorem, they show this theorem geometrically, and they were asking in the same paper, they were asking for a combinatorial formula of these j coefficients that is manifestly positive in the sense of this theorem. So I want a combinatorial model where each of the term I can clearly see that the weight is of linear forms in this way. Okay. So my main theorem, which is exactly the title of the talk, which you should be able to guess by now. So my collaborator Tani and I, we gave a positive combinatorial formula for these coefficients in terms of increasing chains in Bruhat order. So there's an example of an increasing chain. I'll explain slightly a little more in Bruhat order. So Bruhat order is just the partial order on Schubert variety containment. And an increasing chain is just a sequence of permutations that are comparable in that order. And so you see I have like stacks of permutations, and then each of them I can assign a weight. And then each of the weights, you can see that all of the terms over there are linear forms that satisfy this condition. So then this gives a positive combinatorial formula for the double element Greene coefficients. Right. And that's all I want to share. Thank you very much.
Are there any questions?
Have you thought about the K-theory?
No. Yeah, I don't know how to do that.
Definitely ahead of schedule, so we have time for another question.
Maybe I can say one more sentence that these coefficients, they can recover Schubert structure constants for separated descent. If you're interested.
Oh. Okay. All right. Let's thank Jack again.